The race to answer this question has brought some of the greatest scientific minds together in a common goal, a goal that promises to transform our understanding of the universe. Join us as we explore the cutting-edge research that's bringing us closer to the truth, and discover why the quest for quantum gravity is the most important scientific endeavor of our time. At some deep level, all physical laws should emerge from a single coherent theory. Most physicists believe that this theory will be a consistent marriage of two separate ideas that so far have seemed incompatible: general relativity and quantum mechanics. General relativity describes gravity as the curvature of spacetime caused by the presence of mass and energy. On the other hand, quantum mechanics explains the behavior of matter and energy at the atomic and subatomic level. These two theories have been remarkably successful in explaining the phenomena they were designed for. However, when it comes to explaining phenomena where both gravity and quantum mechanics play significant roles, such as near black holes or the very beginning of the universe, they seem to be at odds. This conflict is not merely theoretical. It represents a real-world problem for scientists. For example, our current understanding of physics breaks down when trying to describe what happens at the center of a black hole. Now let's fast forward to the present day. We have come a long way in understanding the fundamental forces of nature. Yet the origin of gravity remains a mystery. Why does gravity behave so differently from the other forces? Is there a deeper underlying theory that explains this phenomenon? The answer to the second question is yes. Such a theory is called quantum gravity. But here's the catch: no one knows what it is. Despite decades of effort, physicists have been unable to develop a theory of quantum gravity that fits all observations. But now, thanks to recent advances in condensed matter physics, it appears as though we may be close to solving this riddle. What if the key to understanding gravity lies not in the vast expanse of space, but in the seemingly mundane realm of tabletop experiments? A group of researchers from the University of Amsterdam has proposed a groundbreaking approach that could forever change our understanding of the universe. Their idea: simulate the conditions necessary to observe the quantum properties of gravity in a laboratory setting. It sounds almost too simple to be true, doesn't it? But don't be fooled. The implications of this proposal are nothing short of revolutionary. But wait, what exactly do we mean by quantum properties of gravity? Well, according to Einstein's theory of general relativity, gravity is nothing but the curvature of spacetime caused by the presence of mass and energy. Spacetime is the fabric of the universe, and everything we know exists within it. In Einstein's theory, spacetime is a smooth, continuous entity without any but in the quantum world, things aren't so neat. Particles can be in two places at once. They can tunnel through barriers, and their positions are inherently fuzzy. So what's the fuzziness of spacetime itself? Can spacetime be in two states at once? If so, this could explain the bizarre behavior of gravity in extreme environments like black holes or the Big Bang. But how can we possibly test this idea? Here's where the brilliance of the Amsterdam researchers comes in. They propose creating a simulation where spacetime behaves like a quantum mechanical system. By simulating these conditions on Earth, we could observe the quantum properties of gravity without having to travel to extreme environments. Now I know what you're thinking. How can we possibly simulate such extreme conditions on Earth? Well, it turns out that we've actually been doing this for years. You see, the conditions near a black hole or at the Big Bang are extremely hostile, making direct observation nearly impossible. But we can mimic these conditions in a lab by using ultra-cold atoms to simulate the extreme gravity near a black hole. This technique has already been used to study how matter behaves under such conditions and has yielded some surprising results. But what if we could take this a step further and actually observe the quantum properties of spacetime itself? That would be a monumental achievement. But why stop there? Quantum simulations could also help us understand the Big Bang. By recreating the conditions of the early universe in a lab setting, we could observe how matter and energy interacted in those first few moments after the birth of the cosmos. Imagine being able to witness the creation of elements heavier than hydrogen and helium, or observe the formation of the first stars and galaxies. It's a mind-boggling prospect. You might be wondering, how accurate can these simulations be? And the answer is incredibly precise. With the right experimental setup, we can create a simulation that accurately models the behavior of gravity down to the smallest quantum fluctuations. This means that we can test our theories of quantum gravity with unprecedented accuracy. And here's the best part. We're already on the cusp of making this a reality. Researchers at the University of Amsterdam are working tirelessly to develop a simulation of quantum gravity using ultra-cold atoms. The experiment is still in the early stages, but the results so far are incredibly promising. Who knows what discoveries await us in this brave new world of quantum simulations? Let's talk about another exciting avenue of research: analog gravity. What if we could create artificial gravity in a lab setting by using sound waves or other types of disturbances to mimic the effects of actual gravity? It might sound far-fetched, but it's already being done. Researchers have created artificial gravity in a lab by using a superfluid to generate sound waves. By controlling the strength and direction of these sound waves, they've been able to simulate the effects of gravity on small objects. Not only does this technique allow for the study of gravity in a controlled environment, but it also opens up new possibilities for testing theories of quantum gravity. It could also help us understand the behavior of matter in extreme environments like black holes or neutron stars. Plus, who knows, maybe it'll even help us one day create our own personal Star Trek transporters. But seriously, it could revolutionize our understanding of the universe and its fundamental laws. While the idea of creating artificial gravity might seem like something out of science fiction, the reality is that it's already happening in laboratories around the world. One of the most exciting aspects of this research is that it could lead to the development of new technologies that we can use to explore the universe in ways we never have before. For example, by creating artificial gravity, we might be able to simulate the conditions inside a black hole and observe what happens to matter under such extreme circumstances. This could help us test our theories of quantum gravity and ultimately our understanding of the fundamental laws of physics. Additionally, this technology could have applications in fields such as space travel and medical science. For example, by understanding how to create artificial gravity, we might one day be able to mitigate the negative effects of zero gravity on astronauts during long space flights. Or we could use it to develop new treatments for conditions that affect people in low-gravity environments. In conclusion, the quest to understand quantum gravity is one of the greatest scientific challenges of our time. But with each passing year, we come closer to unraveling the mysteries of the universe. Who knows what the future holds? Perhaps one day we'll be able to harness the power of quantum gravity to propel ourselves to new heights of understanding. Maybe we'll even find a way to use it to our advantage, harnessing the power of the cosmos like never before. As we continue to explore the depths of space and time, one thing is certain: the journey to understand quantum gravity will be one of the most exciting adventures in the history of science.